Right, these are the solutions for Chapter 7, numbers 17 through 20. Number 17, we have a helicopter lifts a 72-kilogram astronaut. Uh, 15 meters vertically. Straight up. By means of a cable, the acceleration of the astronaut is g over 10. It would also be upward. How much work is done on the astronaut by the force from the helicopter and the gravitational force on her? Just before she reaches the helicopter, what are the kinetic energy and speed? Okay, and we're doing it, is it from rest? I think we would have to assume that. Okay, so force diagram. We know the gravitational force would be mg, which would be 72 times 9.8. So about 706 newtons. And we know her acceleration, or this is the lifting force, or you could call it tension if you want, whatever you want to call that. The sum of all forces acting on her is the lifting force minus the gravitational force. So mass times acceleration, which is g over 10, is equal to the lifting force, which we don't know, minus the gravitational force, which is 706 newtons. So her mass is 72 kilograms times g over 10. We're trying to find the lifting force, so to add this to this side, plus 706 newtons is about 778 newtons. And we were expecting that to be bigger, right? Because we know that she's accelerating upward, so that would have to be winning. Right? So now I think we can answer all the questions. Part A, the work done by the force from the helicopter. The force from the helicopter is lifting her up. So that force, 778 newtons, times the displacement of 15 meters. It's about 11,700-ish joules. Part B, the gravitational force on her is going to do negative work. That's 15 times 706. So that's about 10,600 joules. Negative work. What are her kinetic energy and speed? Well, if this is the net work, remember that net work is equal to change in kinetic energy. The net work done would be this plus this, right? This is the work, this is the work. So 11,700 plus negative 10,600. The net work done on her is about 1,100 joules. So that would be the increase in her kinetic energy. And if she started from 0, that means that is her final kinetic energy. So that'd be the answer for C. And then D, what's her speed? Well, 1/2 m v squared. V squared is equal to her final kinetic energy. So we're looking for the square root of 1/2 of 72 is 36, so 1,100 over 36. So about 5.5 meters per second. right? We could have done all of this, or I guess a lot of this. We could have done C and D with kinematics, since we knew this acceleration. We knew this. Initial velocity was 0. We could have found these that way, but I like this energy approach. It's much more efficient. Energy efficient. All right, number 18. So we're going to lift this roof that has a weight. Weight is the same as gravitational force of 360 kilonewtons. And we're going to lift it up by 10 centimeters. And how much work is done on the roof by the forces making the lift? Well, they would have to counteract the gravity. They'd have to lift it through that. So the work done by the lifting force would be equal to 360 kilonewtons times 0.10. That's actually that easy. 360, let's see, probably 0.1, 360,000, so that'd be 36,000 joules. Is that part A? Part B, same idea. We have a woman who is lifting a car, 4,000 newtons, and she's lifting at 5 centimeters. That is it 200? Is that right? Let me just check that. Something looks funny about that. 4,000 times 0.05. Nope, that's right. Oh, 200 joules. Number 19. So before we do 19 and 20, just point out that since the change in kinetic energy is equal to the net work that is done, then if we can determine the net work that's done, we can get right at that kinetic energy. And in number 19, we have a block that is sliding through a displacement of 0.5 meters and along an incline, and there's a force acting on it, a tension force up the ramp, and then gravity is pulling down the ramp. Since its kinetic energy is increasing, we think that means it's accelerating down the ramp. So that would be the work net would be the work done by gravity down the ramp, and minus the work done by the tension force, which is pulling it up the ramp. So that gets us right from here to here. So if I can figure out this gravitational force, but it's not all of the gravitational force. I need the part of the gravitational force that's down the ramp, right? Since this is the displacement here, and the gravitational force would be down. Or I guess you could say, oh, since those are not in the same direction, I could say the work done by the gravitational force is gravitational force times the displacement times the cosine of the angle between them. That would be that angle right there. And notice that that's not the same as the ramp angle. That's the angle complement to the ramp angle. So let's see. The ramp angle is 50 degrees, so this would be 40 degrees. So that's, let me go back to here. So 1/2 mv squared is equal to the work done by gravity. That's going to be positive work, which is mg d cosine theta, where theta is, you know what, I shouldn't call this theta, should I? I should call this phi, because theta was already taken for the ramp angle. I call that phi. Minus the work done by tension. The tension force, it has a magnitude of 50 newtons, and that's the same d. So we can start filling some stuff in now. Oh, and we also know that its kinetic energy increases, so I guess we know they're telling us that this whole thing its kinetic energy increases by 80 joules. Oh, here we have mg times 0.5 times the cosine of 40 minus 50 newtons times 0.5 meters. Right? So how much greater would its kinetic energy have been if the rope had not been attached to the block? Well, this, you know what, I think I made way too much out of this problem. I did way more work than was necessary. This is all correct, but the difference is that instead of having this much of the energy taken away effectively by the rope, then all of this energy, if there had been no rope here, then this would have to increase by this much. Right? So this is the work done by tension. So if that hadn't been there, then the increase in kinetic energy would have been that much more. So that means that the kinetic energy would have been this much more. So is that 25 joules more? So all this reasoning is correct, and we could have done more math here. This number, in fact, it didn't make any difference at all to our calculations. Right? I think that, yeah, since we don't know the mass, and I think doing this, we could actually figure out what the, no, I guess we couldn't. I was going to say we could figure out the mass of the block or the angle, but I guess we would have to know one of those to figure out the other. But we did have enough information here. All right, number 20. This is similar to 19. So if that kind of made sense to you and you didn't get 20, you might want to pause now and just take another look at 20 before you watch what I'm going to do here. All right, so block is sent up a frictionless ramp. So imagine it's sent up here within some initial velocity, v sub 0, and it will slide to a certain point, and then it will stop, and it will come back down, right? So they're giving us a graph of this. The initial kinetic energy is, where is it? 40 joules. And the displacement it's going to go through, delta x, is 2 meters. Right? And they want to know what's the normal force on the block. So let's see what we can figure out here. I know that the change in kinetic energy is equal to the net work. And the net work is being done by the net force, in other words, the sum of all forces, times the displacement, and those will be in the same direction. So what is the net force on this? If we made a force diagram here, the net force is just the sine component of gravity, right? So the change in kinetic energy, well, it's going to go from having this much kinetic energy to not having any. So its final kinetic energy will be 0. Its initial kinetic energy is what it started with, the 40 joules. And that's equal to the sum of all the forces here. The only thing that's left is the sine component of gravity. So that's mg sine theta times d, which is 2 meters. And oh, we also know the block's initial speed is 4 meters per second. So that means here that if this is 4, then 40 joules is equal to 1/2 m times 4 meters per second squared. So I think we can find the mass then, can't we? So the mass is, that's 16, half of 16 is 8 times, so it'd be 5 kilograms. And if I know that, I think I can come back here and find the angle, the ramp angle. So let's see what we have. We've got -40. This would be, the work here is this, the force, the net force is this way, and the displacement is this way, so this would be negative work here. I left out that negative sign. I caught that because I saw that one of my sides was negative and the other wasn't, and that doesn't make any sense. So let's switch the sign on both sides. The mass is 5 kilograms times 9.8 times 2 times the sine of the ramp angle. So the ramp angle is the sine inverse of get in degree mode. Oops. Degree mode, so I want the sine inverse of 40 over 10 times 9.98. That's about 24 degrees. And now that we have that, we can find the normal force. The normal force would be equal to the cosine component of gravity, mg cosine theta. So the normal force is m g cosine theta. So I'll go ahead and take the cosine of that angle times 5 times 9.8. That's mg cosine theta. So it looks like it's about 44.7 newtons.